That or 2000.
So it's like they're like that, yeah. The brown one is made of cattle.
Oh, the Canada, I would.
So the cattle is made of them. Of the
I think so. That's cool. Different. You gotta buy some dresses. It's always dresses, and then you gotta go look for some. You like that rap a little written?
It's like a
Yeah.
You know,
You know what you
Good afternoon. Do you have any questions? Today I'm using this question for today's attendance question. So if you want to make the function continuous, you have to make sure the number a and b. These are numbers that will put aside in order for the function to be continuous. So the ultimate goal is to have the left side connected to the middle and the middle connected to the right. The function, this are all linear function or polynomial. The function itself is continuous, but its continuity is at the end of the interval, at the end of that piece of the function. So, like this question, the problem will be when x equals -1 or when x equals 3. So x equals to -1 belongs to the first one. You're calculating the left limit at -1. If you're calculating the right limit at -1, you have to use the second equation. And if you want to make the function continuous, the left side equation has to be equal to the right side equation. So that is one equation. And the continuity is the only reason that we can decide A and B in the equation. For example, we would say for the function to be continuous as -1, we have to have for f of x continuous, that's x equal to -1. We need to have the left side limit, left hand limit equal to the right hand limit. The left hand limit is -1 squared. Who's going to follow the x squared for the left hand limit? That actually equals 1, right? And then this is a left hand limit. It got equal to the right hand limit. The right hand limit is when x is bigger than -1, and then you will use this. And you're going to plug in the -1 for the limit calculation. So if you plug in -1 to ax plus b, it's -a plus b. That's the continuity at -1. Now, to make the function continuous, continuity at x equals 3, to make sure the function is continuous at 3, we have to have this symbol 3, this symbol 3. This side is the left side of 3. So the left side limit to 3, you would put in this equation. You're going to put in x equal to 3 for that one. So the left hand limit at 3 is 3a plus b. That's the left hand limit at 3 of the piecewise function, piecewise defined function. Now the right side limit, you have to plug in 3 in to the last piece of the function, because that says x is bigger than 3. So you've got to find the right hand limit of the function at 3. You have to put in 3 to the last equation. That actually equal to 9. All right, so combine the two, we end up having a pair of equation, and that's really how we can solve for A and B. And then you're gonna take on combine the two equations. So we have one equation that says 1 squared negative 1 is 1 equal to negative A plus B. Right. The second equation is 9 to 3A plus B. So these are really for continuity at -1, you got one equation. For continuity at 3, we have one equation. There's two equations. And to find the A and B, this set of values. Right, so let's try to figure out how to solve this kind of equation. It's called a system equation, right? So how do we solve this kind of equation?
For the top by 3, that way it becomes negative 3A. Cancel out with 3A.
Okay,
You just add 3B to B.
so we multiply the top equation by 3. It will be 3 equal to negative 3A plus 3B. So that becomes the first equation becomes this, and that would
Subtract 3A.
or add.
Yeah.
Okay, so now this is actually the first equation, right? This is the first equation after we multiply the two, so that's still the first equation. This is the second equation. Right, so what we're gonna do, we're gonna add the first equation with the second equation. We're gonna add them all together. So if you're adding them, then the negative 3A, add the positive 3A equals 0. Like the negative number plus positive number equals 0. So then the left side is 12. The right side is 0 plus 4B. So you add the two, B plus 3B. They're like terms, they're all equal 1 equal B. So that allows you to cancel the A. We have two variables, A and B. But because we combine them this way, one of the variables is gone. So we have this equation. What do we do next? 5 by 4. So B plus 3. Once we have the B plus 3, how do we solve the other variable? We have one number.
Just plug in 3 to the original problem.
Okay, so we can plug into like the first equation to solve for A. So this is the overall steps for how do we solve this kind of question. So we're applying the fact that we hope the function is continuous. That's how we end up having this equation. And then the rest of them is algebra to solve the equation. Some changes to the function allows us to solve this equation. So let's submit the answer for the attendance for today.
Yeah, I told you. You already know what.
One of the questions that we had on the continuity, the 1.5 is kind of like this because that function has only one.
They're not here. Oh, no, he is.
Yes, B. B equals 3, A equals 2. Any question from the homework? Any homework question?
Huh?
Any question?
Oh, no.
So today, let's try to finish 1.6 and possibly start 1.7. All right, there's a graduate student panel today. I posted it. I'm sure if you didn't talk about it, you guys have consider graduate school or not, but it's going to be at, so these are people that graduated from our school or attending graduate school. It's today at 6:30 and people's problem 112. I think they offer pizza like at 6 o'clock. So we invited a couple of speakers to talk about how to prepare for graduate school. What is it like to go to graduate school? If you have any questions or want to share some experience from them that you want to attend, or if you just want to find somewhere to spend your dinner time. Get to mention that 4 minutes today. All right, yesterday we started talking about limit at infinity, but most of them have infinity as a limit, but now we're gonna talk about limit at infinity. What is limit at infinity? That is not only a limit calculation, x is approaching a finite number. So we will have like limit of x squared, x approaching 1, which equals 1. So you will have L is a number for the y value, C is a number for the x value, and you're calculating the limit of the function. If x goes here, where does the y goes to? But limit at infinity is you switch out the C, the notation C for infinity, and then figure out when x goes to a really, really large number, what is the y value goes to? If the y value is going to a finite number, then we have a horizontal asymptote. So that's what the main thing that we're talking about. Limit involving at infinity is the topic that we were talking about yesterday. If you have infinity as a limit value, you will have a vertical asymptote. If you have infinity at the x value, and suppose you got a finite number, then that will be a horizontal asymptote. So there are a couple of terminology that we can talk about if we have limit at infinity. So this is expanding what we have already started talking about yesterday. So then look at the positive infinity and negative infinity separately. The positive infinity is really when x goes to the far right of the number line. So take the right side behavior of the function graph. If x goes to negative infinity, it's the far left of the number line. You got a number line for the x value. Left 0 in positive infinity. So negative infinity, 0 in positive infinity. So if x is approaching infinity, we're saying, so we're trying to make up a formal definition for this. In the past, we have epsilon delta definition. That is when x is finite and the y is finite. But if x goes to infinity, x is not going to a finite number. Therefore, we don't have that delta. We don't have a small range. We actually are letting x go to a bigger number as the limit goes up. So we still have a finite value for the y value. So f of x minus L is still there. F of x minus L is still less than epsilon. So epsilon is a tolerant level between the target value and the function value. But we don't have delta anymore. Instead, we use the letter m. And represent a large positive number. When you see x is going to infinity, you're using this number to explain how large is x considered large enough so f of x will be approaching the letter L. So we will say for any epsilon, you can find a large number m. Whenever x is bigger than m, we'll have f of x minus L is smaller than epsilon. So whenever x is large enough, these two are really close together. That means that's indicating that if we want f of x to approach L, all we have to do is to make x larger than such a big number m. That's the way to describe how large, how is x approaching infinity. So we have a similar definition. This is a limit definition, the formal definition for infinity, limit at infinity. If x is approaching, if x is going to negative infinity, that means x is really large, but negative. So we are choosing a large negative number to indicate how large x has to be for the limit to satisfy that tolerance. So we're choosing, we would say for any epsilon, we will find a big negative number. Whenever x is smaller than negative number, then f minus L will be close enough to L. All right, so these are the definition for the one-sided limit, one-sided to the positive limit, one-sided to the definition for the positive infinity and definition for limit at negative infinity, and then we have a double-sided limit. Suppose these two are equal to the same thing, then we have two-sided limit. All right, whenever this is happening, we'll say that the if this is true or this is true, then we have the horizontal asymptote. This we already defined it yesterday, but the horizontal asymptote is a horizontal line. That's why we have y equal to a number to the limit value. Now, if this limit does not exist, of course, if the L, if you cannot find a finite number, then we do not have a horizontal asymptote. But as long as the L is finite, then we have a horizontal asymptote. Any question? Right, so this is just to make it formal. Yesterday we started. I would say as long as the limit is finite, we can find it, then we have a horizontal asymptote, but it's providing the formal definition of it. All right, this is something that we have already tried it yesterday. I don't know if you remember, what was the horizontal asymptote for this? What's the horizontal asymptote? Do you remember? The limit at infinity, what is it? Do you remember? No.
One,
It's 1. How do you know it's 1?
because the four kind of becomes irrelevant once the numbers get really big.
Yes, exactly. When the x is going to infinity, the 4 becomes irrelevant or almost negligible because 4 is so small. If x is infinity and 4 is very small. Therefore, this is like x squared over x squared kind of thing, at least at the infinity, that's what's going on. So the horizontal asymptote is 1. And you can see it by graphing it, but for now, we're trying to make sure that we're able to describe it with or without the graph. So if you get this function, you have y is 2 x squared, and then divided by x squared. I used the x squared over x squared is a horizontal line, but if you put plus 4, all right, that plus 4 causes the denominator to be bigger than the numerator. If the denominator is bigger than the numerator, you're having a small number divided by a big number. So, of course, the number is less than 1. So, right in the middle, if x equals 0, you have 0 divided by 4, that's 0. So, dip down. I mean, this side is 1, that side is 1, the middle dip down a little because that plus 4. So it kind of change things a little. You can also make it different. For example, what if it's 40? What if it's 400? Right? It doesn't change much. The overall behavior at the far right is still 1. What it changes is the curve in the middle becomes bigger, like longer. But if it's small, like 1, that changes very small region. But overall behavior will be the far left and far right, which is horizontal asymptote, will still be there, and then the number that you can change that controls the middle, the local behavior along here, is caused by change by the coefficient. That's what we're getting this. So somehow we do try to change things a little to see what's constant, what kind of changes it's gonna happen. Right, so this is one example, and a couple more examples. This question is x divided by x squared plus 1. So we also have a horizontal asymptote. I'm trying to get some pattern from here. So if you have f of x equal to x over x squared plus 1. Okay, so when you have this, you see the numerator is smaller than the denominator in terms of degree. So if you look at limit x over x squared plus 1, if x goes to infinity, what is this? X over x squared. What's this limit? What's this limit in the picture?
Oh.
It's 0, yes. So if you look at the differences in the numerator and denominator, numerator is degree 1, denominator is degree 2. So the numerator have a lower degree in the denominator, which means when x goes to infinity, the numerator is infinity, denominator is infinity squared. So the infinity are not equal sometimes, at least in the degree level. So if numerator is 1,000, denominator is 1 million. So you can see that why this whole thing will go to 0, because x doesn't make a difference. So you have a large number, but you have a much more larger number in the denominator. The fraction actually goes to 0. It's this example. We can see that the whole thing is connected because there's no asymptote. You can see if we try to make the denominator equal to 0, denominator is x squared plus 1. If you make it equal to 0, so there's no solution because this x squared is positive. X squared plus 1 is always bigger than 1. So x squared plus 1 equal to 0 is no solution, at least no visual, no real solution. You can force us to find a solution. You get x squared equal to -1, and then x equal to positive or negative I imaginary number. So this is a degree 2 equation that also has a solution, but it has all two complex solutions, and they will not show up in the picture because they're not real. But basically, we say there's no real solution, therefore we don't see any virtual asymptote. We have no virtual asymptote. All we have is a horizontal asymptote. Other things that it seems to behave very similar to, x over 1, right? 1 over x. So it has a similar behavior to y equal to 1 over x, except the middle there is caused by this causes the denominator no longer have any asymptote. This one has asymptote, so it looks like this. Right? So overall, it's similar to this, except in the middle, right? So the numerator have a degree 1, this is degree 2, and now this is degree 0, this is degree 1. So degree denominator is 1 degree higher than numerator. And that's kind of the reason that this two actually have similarity. But yes, they do. This one do have virtual asymptote, this one do not. These are some of the patterns you can observe. Another example, this question is you have numerator is x over, and copy this over to. Okay, so this one, this is x over y equal to x over x squared plus 1. Okay, we were talking about something similar to this. If you're trying to find the limit of this, limit of x over square root of x squared plus 1, x goes to infinity. What's this limit, What's the limit? What's the limit? It's going to be 1. And do you know why it's 1?
Because the square root and the square cancel out, so it's essentially just x over x.
Yeah.
Right, yes. So this is actually the same as the limit of x over square root of x squared, which is equal to the limit of x over x. That's when x is positive, infinity. And that's why it's equal to 1. We can only do this kind of changes when x goes to infinity. For example, if x goes to 0 or x goes to 1, then we cannot do this. And they are only comparable if x goes to infinity. And that's something to watch out for, because occasionally it has to change it even when x goes to a finite number. If x goes to a finite number, the first thing we'll do is to substitute, right? Use that number actually in the calculation. Is infinity that sometimes we have to think about ways to reduce the equation. This is this example. This is another example, the sine x over x. The limit, the function is undefined here, but then it does have a limit value of 1, and this is sine x over x. You can see a lot here. This one also have a horizontal asymptote that's over here. Because the function's oscillation gets less and less, the amplitude of the wave gets smaller and smaller. So it started with a big wave and then smaller and then smaller. Eventually it start like going up and down. So eventually in the far left or the far right, it does have a horizontal asymptote because the denominator is causing the number gets smaller and smaller. And the numerator is finite anyway. So sine function is always bounded by -1, +1. All right, so I'm going to look at something that we mentioned yesterday about a degree of the numerator and denominator. This is an example explaining the reason why that would work. So for example, let's say we want to find the limit of this. All right, one of the things that is we can see the reason why we would want to pay attention to the highest degree. So you see, this is the example when the numerator and denominator have the same degree. So what we can do is we can get the cube function out of it. So if we divide every single one of them by x cubed, and that's 1 over x cubed is being divided out. So if you divide every one of them by x cubed, it's like multiplying 1 over x cubed to the numerator and the denominator. If we do divide them all by x cubed, it will look like this. Right after we divide every single term by x cubed, then the first one becomes a 1, this becomes a 4. But what about all the other ones? You will have this divided by x cubed is 2 over x squared, 1 over x cubed. So these all have a denominator. So we know if the denominator goes to infinity, then 2 over infinity is 0. So that has 0, this is 0, this is 0, this is 0. Because the denominator is so large and each individual term goes to 0, the whole limit is 1 over 4. So only the highest degree actually is now comparable to a finite number. On the other one, when x goes to infinity, actually equal to 0. So this is just an illustration why we only want to care about the highest degree, because all the other ones not comparable to the cube function. Once we divide by the cube, the other one has pretty much a 0 limit. And that's one of the ways to illustrate the point. So this is what we have already mentioned yesterday. If you got a two polynomial, one in the numerator, one in the denominator, you would only worry about comparing their highest degree. If the highest degree are equal, then they get all the other ones are ignored. These two are canceled, so only the coefficient an over bn is the m equal to n, right? A over bn is the answer of the limit or the horizontal asymptote. Let's see a horizontal asymptote. Now, if the numerator have a lower degree, the numerator is much smaller than the denominator, the limit equal to 0. So y equal to 0, which is the x-axis, will be the horizontal asymptote. Last case is when the numerator have a higher degree, and that will be when the numerator is way too big, and then we would say there's no horizontal asymptote. Since the whole function goes to their increasing. So then they don't level down, they just go that way, go that way. There's no asymptote. Any question? Let's look at a couple of exercises. Okay, so let's see this one. What's the limit? What's the limit? The first example. Which case, right? Are they equal? Are they small? Are they big? What is it? This one has a limit of 0. This numerator have a lower degree than the denominator. The second case, the limit. Question 2. Huh? What's the height degree in the numerature? Right? See, so sometimes we have to reorder them. So the solution is 1 over
Negative
negative 3. 1 over negative 3, yes. The last one. It's
Just two.
no.
Wait, no.
Yes, this one does not have a horizontal asymptote. But the limit value actually equal to, you see the x goes to infinity. So this one is gone. Let's write it out. All right, because of the degree, we can quickly determine the first one has a limit 0. This one has a limit of 1 over 3. This one numerature have a high degree. It does not have an asymptote, but we should still determine the limit. So limit equal to, remember the finite term compared to infinity, they're negligible. So we only are concerned with the one that has highest degree. This numerature highest degree is x squared. The denominator, the highest square is negative. The highest degree is negative x. Right, and then we can start cancel the common factor. Cancel x. So it's the limit of x squared cancel x is x over negative 1 or negative x. Negative x. And x goes to infinity. So the function goes to negative infinity. X is infinity, x is having infinity limits, so this is negative infinity. So the answer is negative. Any question? Right, so that means on the far, this is our, on the right side it goes down. I believe on the left side it goes up. Visually it will look like this. You see the negative x there? When you're ignoring the number term, this is negative x. So the overall behavior of the function looks like y equal to negative x this way. This side goes negative x this way, right? Negative x is decreasing. So it looks like this. You can also confirm this with a picture. So like this, numerature is x squared plus, what's it? X squared minus 1, 3 minus x. All right. Minus 1. And the denominator was x. That's what it looks like. So the denominator is 3 minus x. So x equal to 3 is a vertical asymptote, but it doesn't have a horizontal asymptote. What it does is, you see, that one goes that way, this one goes this way. So on the positive infinity, it went down, it goes down. So that's negative infinity. On that side, on the left side, negative infinity, it goes to the positive. So it's infinity and infinity. And that's this is what we're calculating in the calculation. That's so that's on the right side, it goes to negative infinity. If you're calculating limit when x goes to negative infinity, and the y actually goes to a positive. Okay. So I'm saying it goes like this side goes down, that side goes up. So it looks like at the left and right behavior. Any question? This example. A couple of other things I want to give some examples. Other than polynomial, all these summary that we have here is about if you have a polynomial divided by another polynomial. And then what if we get other functions? So let's look at limit of exponential function, limit of logarithm function. We tried a few examples before, and now we just try to make a combined summary of it. The first one says if you have a base that's positive, then limit of a exponential function on the negative side equals to 0. It's a horizontal asymptote at 0. Now on the right side, it actually goes to infinity. If you have some, you still remember a little of the behavior if the function is graph, you might understand this a little bit better. For example, if the base is bigger than 1, exponential function is increasing. So it's same increasing function. So this is a y equal to ax. So for example, y equal to 2 to the x will behave this way. Okay, so you can see on the far left, which is like say limit x goes to negative infinity, e to the x, right? That's equal to 0. And e is bigger than 1. Limit 2 to the x goes to positive infinity, because that goes up. So you can think of it, start from 0, goes on to infinity because it's an equal function. Second rule says if you have a base that's less than 1, then the function is decreasing. So it's decreasing. This would make it complete opposite from the positive, from the a that's larger than 1. So I guess one of the ways to understand them is to, if you can, kind of think of it from the visual representation of it. So the first one is this way. That was 0, that was positive infinity. The second one, if a is less than 1, okay, a like 0.5. So y equal to 0.5 to the power x, it looks like this. It's decreasing. So when you have a negative x, then a to the x actually is pretty large. When you have positive x, then a to the x it becomes smaller. So that's why on the left side, when x goes to negative infinity, it's positive infinity because it's going all the way up. But on the right side, when x goes to positive infinity, it's actually 0. So it almost felt like this one switched to this and this one switched to this. So 1 and 2 summarize the exponential function. The base of the exponential function determines whether the function is increasing or decreasing. If the base is larger than 1, that is increasing. It kind of goes with how we understand. If the base is bigger than 1, such as 1.2, that means we're 2% higher than before, right? If the base is higher than 1, exponential growth, you have 100% or 120% bigger than the previous year. And then the next year is 120% bigger than the previous year. So then the quantity gets bigger and bigger. So it's only understandable if the exponential function base is larger than 1, the function is growing. But if the base is less than 1, for example, we're doing this is actually a decay model. So for example, value of a car, when you bought the car new, maybe 6,000, 60,000. And then the next year it decreased, right? 80%, and then 80% of the previous year. It gets smaller and smaller. So it's only understandable that if the base is less than 1, such as 80% or 70%, the quantity or the value will decrease. Number 3, we actually talked about this a little bit. This is really how we understand logarithm function. Logarithm functions graph, we should see one standpoints. Okay, for example, the exponential function 2 to the power x, say exponential function, and then y equals 0.8. So that's the exponential function to the power, right? So this is the a is less than 1. The red one is when the a is bigger than 1. And let's talk about logarithm function. Y equal to logarithm. So I should erase them so it's easier to see. This is logarithm function. Okay, so logarithm function you have to have positive x. The input has to have positive. We don't have anything over here. Close to 0, things are going down. So when x approaches 0, y goes to negative infinity. And when x goes to positive infinity, this is actually increasing. So the y goes to infinity. And that's kind of the reason why we have this function here, logarithm function, ln. Okay, so it behaves this side is when x approaching 0 from the right side of 0. So the limit is negative infinity. That's the one on the left. The one on the right is over here. So when x goes to positive infinity, the logarithm of x goes to positive. So that's the logarithm function. Logarithm function, the base is positive, bigger than 1, that is increasing. The base is less than 1, it's decreasing. Logarithm have the same decreasing, increasing behavior as exponential function. You remember pre-calculus. Any question? Last one is a little bit about tangent inverse. Tangent inverse is a increasing function. It increases from negative pi over 2 to positive pi over 2. If you look it up, that's why the two limit have pi over 2. It has horizontal asymptotes at those two values. So tangent inverse, right? Tangent inverse. So this has, this is positive 90, this is negative 90. Tangent inverse is an angle, so that's why you have asymptote at an angle. Positive pi over 2 is positive 90 degree, negative pi over 2 is negative 90 degree, so it's increasing all the way up. A couple of special limits. And if we don't remember it, or if they were not introduced, we might not even think about it. But these are the kind of situation that they're not as frequent as a polynomial, but they're still being applied here and there, so that we might have to refer back to them. Any question? Right, here, I mean, negative 90 degree to 190 degree. That's the reading measure, the three measure reading. All right. So this is an example, a tricky example to illustrate that we cannot trust the numerical calculation all the time. We do use numbers to try to find out roughly what the limit is. So sometimes the calculation might not be correct. So for example, this one, if we try to use a number, this is actually a special number. Let's see what the value is supposed to be. Okay, so if we are calculating this limit, we just finished the calculation. If x goes to positive infinity, which is the right side behavior, it goes like this. We have the limit that was pi over 2. So limit of this function equal to 226 over 355. And it's multiplied by, this one has a limit of pi over 2 times pi over 2. Right, so this is the actual solution. So if we're going to find a number, it is this. So what was the number again? 226, 355. Okay, so it's roughly 1.392. That's an approximation.
That's 225.
Oh. Okay, I called that. Oh. All right. Yes, thank you. All right, so that's fine. So the answer actually is this number, which almost looks like a 1. So if you are using number, it might be tricky to the answer is 1, but it's not. So this is a solution at 0. You can see the decimal number. The decimal answer to this is 0.99999 and then 158. So it's not 1. It doesn't equal 1. It's really close to 1, but it's not 1. So if you are using the numerical number to figure out the answer. For example, let's say we use our calculator and we want to have x goes to infinity, and then how do? We can do 226 over 355 most of us have a tangent inverse on our calculator and go tangent inverse of a million or 10,000. Okay, because x is supposed to be really large, x is goes to infinity. You can use x equal to a large number and then go tangent inverse of it, and that's really the power of 2. We got to find a number. I think you get something like 0.9999. Since we're doing number, right, we might be checking to, hey, my number is 0.9999. Maybe the answer equals 1, but it's not. That kind of makes sense. So that's just saying sometimes you can't trust 100% what would say anticipated solution. So the anticipated solution close to 1, but know that they were supposed to be this. It's not exactly equal to 1. That's the true answer there. Because it doesn't equal to 1. But really close to 1, but the exact answer is not 1. I guess this is just one of those cautions. All right, I still feel like numerical calculation is useful and important because if you are doing some real life work, close enough answer to a certain decimal places is already accurate. So I would say if I see limit of this calculation, this limit equal to 1, that won't be too much off because you knew it was 0.9999, right? So it's really close to 1 anyway. So even if the answer is wrong, it's not wrong by 4. But still, we care about the accuracy. You have to pay attention for, like, people ask you, well, let's make it accurate to 6 decimal places. We have to make it that way. Because sometimes the number that we calculate, they end up being multiplied by a million or something. What you were talking about, if you're talking about $1, then 0.9999 is no problem. But if you're talking about $1 million, then 9999, whatever the number after that, is actually important, like it causes big differences. So it depends on the situation, like what we use it for. Okay, a couple of other things. This is whenever you have infinity involved in the calculation, we can also look at it part by part. Suppose we have a numerator that approaches to a finite number limit, and the denominator is approaching infinity. In that case, you have a finite number, finite limit divided by infinite limit, the limit always equals 0. That's one of the scenario. And then we're going for that idea how we are looking at a calculation that involves infinity. You might be comparing the size of the limit. If this is finite, this is infinity, then the limit, the division goes to 0. But if this is infinity, then we cannot make decision. If you know their actual function, like this is degree 2, that was degree 4, then we know it's 0. So sometimes one infinity is bigger than the other infinity. Sometimes one infinity is smaller than the other infinity. Sometimes they're the same kind of infinity. So we don't have to look at the structure and think about more of the detail. And just infinity, we won't be able to make a decision. What is finite? What is infinity? Compared to finite, infinity always causes a big difference. The bottom one says if you got that's for negative infinity. Whenever the denominator goes to infinity, numerator goes to finite. The division always have a limit as a limit value, has 0 as a limit value. Any question? And this is the same reason that we would have that degree comparison. Okay. Let's look at this. If x goes to infinity, do you remember what was this answer? What's the limit, the first limit? What's the limit for this first example? Do you know what the limit is?
0.
0.
0.
Why?
Because you have an infinitely large number of denominator.
Yeah.
Right. The denominator is very large, the numerator is finite. The finite limit infinity will always have 0. What about this one?
Is that the same thing? Because you can't do the inverse of the large number.
Okay, yeah. So the answer is limit is
Is it?
What's the limit? You can calculate it. I mean, you can make x equal to 1,000. Cosine 1,000 divided by 1,000 plus e to the 1,000.
Cosine is always between -1 and 1, right?
Yes, cosine always is finite. So the limit is 0? 0, yes, that's right. You can confirm this with the calculation. Even 10 will make a difference. You go cosine 10 divided by 10 plus e to the 10. And you see that number is really small, like almost 0. So exponential function causes the number to be much larger. So e to the x goes to infinity, and then when you are sure it's finite, the limit actually equal to 0. So this is most of the question I have in 1.7. We are only 10 questions, about 10 questions in 1.6, so almost signing. Did we finish 1.6? Yes. 6. Let me. I will assign 1.7. Let me also send the example. I haven't really assigned it yet. Okay, so this is a 1.7. Let me assign this so you can actually see on your side. This was assigned before. Today is the 25th. Let's give it a week. All right, you should be able to see on your side, so we can try a few questions together. The first question has a graph. I'm not sure if we all have an identical graph, but I'm going to use a graph to understand the limit calculation. And the first view, limit when x goes to finite number. The last two is when x goes to infinity. Yes?
My login isn't working anymore.
Oh?
I don't know. It keeps telling me that it says your session has timed out due to inactivity.
I think you might have to refresh or delete the cache, because last time it was automatically logged out. The page is saved in there. So you have to refresh your browser. Or you can use different browser. You know how to clear cache? Store the pages.
I don't think so. So you can just like go all the way out?
Did you log out?
No, I don't think so.
Okay.
That's my password.
Yeah, I know. This is a save the page on your computer. Can you go to like setting or something? You just have a setting.
On here.
Yeah. You have to go online, Google how to clear cache on Safari.
Oh, right.
Because your computer has saved some pages and it's using that page over and over. You're going to use it into a page. You want to eliminate all the pages that you visit the website. It's your new page. Like this. How to clear cache. Right, I think that's what you need to do. So just to try to clear some data in cache, so then they'll force the computer to load out a new page.
Okay.
Right, the first question, this is when x approaches -5. So you want to zoom into the picture to find what's going on at -5. This is 0, so you're going to count 1, 2, 3, 4, 5. -5. So you can see at -5 when we have a vertical asymptote that you with me. And -5, we're okay there. So maybe I can copy over the picture. You can actually record it. All right, so -5 is right here. 1, 2, 3, 4, 5. So you can see at -5, on the left it goes up, on the right it goes down. So here is a positive infinity, this is a negative infinity. And then the one after that is at -3, which is over here. And -3 it goes up to positive. So that's the answer for the first three. Do you have an identical question? Are you able to finish the first three questions? Well, did you figure out how to get the page after refresh? You're refuse to refresh. That's what's causing it to. You figure out how
That's what I'm
to.
trying to.
Select preference and then click on advanced tab. No, I think it should be in Safari, but not in this page. And for the history view, clear the history.
Mine put history.
Yeah, let's see if that works. So then you go close this page and then did you bookmark the website?
Yes, I did.
Then you can pull them up from the bookmark. Let's try. Okay. Yeah. So it looks like clear history might help. Okay, let's see. Were you able to finish the first three? We would have negative infinity, infinity, negative infinity, because those are asymptotes. So we would go, let's see how we enter. Which way do we do? We'll try infinity, I and F, and then negative infinity. And this one is -3 is infinity. And then the far right, the right side is going all the way to, this is -1. So I would say this is -1. And then on the left, it looks like the oscillation is getting smaller, so it looks like a +2 on the left side. And then of the pictures, that's all 5 answered. Do you have a different picture or do you have the same?
Mine's a different number.
Right, so you can see the -5 has the asymptotes, so that's why the positive infinity, negative infinity, and -3 have the positive infinity for both left and right. This is a right side limit, and this is the left side limit. That's my answer so far. If you have a different version of it, and you have any issue, I can look at it together with you.
Oh, no, you're fine. I just had a question.
Mhm.
So with it being at the numbers, like it says 2, -3.
Mhm.
So with -3, with it just being in the middle, since it's a vertical asymptote, since they're both going together, it's always gonna be positive infinity?
Yes, yes, they're both going up. They're going to the same direction.
So what about if they're not?
If they're not, it will be the same as what happened at -5. One up, one down. So we have a one-sided limit. We don't have the two-sided limit.
Yeah, so like mine says left of -1, and then, so basically where 5 is, mine says -1,
Uh-huh.
except, so there's one going up and one going down, but it says when it's at -1, not positive from the left side or right
That
side.
will be D and E. If you don't have the direction, then it will be D and E. Let me see
Okay, that's fine.
which one. -1,
Yeah,
right?
-1. So if one going up and one going down, so we can.
Yes,
Okay.
the two-sided limit. Any other question? Your question number one. Okay. Yeah, so a -1, which is right here, is infinity, right? So the left side is going up, the right side is going up, so it's like infinity. Oh, your has 3. Mine was at 2. 1, 2, 3. So the last one should be a 3.
What do you count?
Yeah, see, mine is like you try to find the center line of the fluctuation. Mine is fluctuating at +2. You find the line, a horizontal line. But if you draw a horizontal line first, that was a 1, 2, 3. So yours should be a 3 on the left. Any other questions for question 1? So this is question 1. We really based on all the calculation based on the graph. Question number 2. Another graph. The picture. Let's see. Did you look at yours? Do you have the same? The same. No, we don't have to differentiate. So the first one is A. A is the function limit the far right. So A has x goes to infinity, which is right here. Left infinity is right. The right. Positive infinity is what happens at right? So then we have 1, 2. So limit should be 2. So for A, the answer should be a 2. Hope you're with me. The second one is the one when x goes to negative infinity. That would be the one on the far left. That was, what is this? What's -2. So then that will be -2. C is when x approaching 3. So I think 0, 1, 2, 3, right? Which should be infinity. So the C is a infinity. And then what about D?
Negative infinity.
Negative infinity. All right, and then E was at 2.
It's also negative infinity.
Negative infinity. Okay, thank you. And then F is equation of the asymptotes. We got a bunch of asymptotes. They were whenever you had infinity. So this is an asymptote. This is an asymptote. This is an asymptote. Those are all x values, right? X. So all the vertical lines. That's -2. One was 0. And that one was a +3. And then the horizontal asymptote is when you have the first two, the 2 and -2, the horizontal line. So we would have y equal -2 and y equal +2 because they're the horizontal asymptote. We identify all the asymptotes and then we can select.
You have to enter I or N for positive and negative. Yeah, it did that.
See, so I enter for negative infinity and then I for the positive. Thank you. So that's number 2. And you can see this assignment really has lots of big questions. This one has the limit of this function by evaluating the following number. You can see there's this is really where we're comparing infinity. Numerator is a polynomial. Putting numbers such as x equal to, I will just go ahead and do 10. So if you put in 10 for x, numerator is 10 squared, which is 100. Denominator is 2 to the power 10. 2 to the power 10 is much bigger than 100. So you can see that exponential growth is growing way faster than the polynomial given to. So in this case, we're comparing 2 types of infinity. the infinity that caused by a polynomial is smaller than the infinity caused by exponential function. So the denominator is way, way bigger than the numerator. Remember, you have a smaller number divided by a big number. The denominator is bigger to cause the number to approach. Do you know what's the limit? It's 0, yes. So whenever we have a small number divided by a really much, much larger number, the answer is 0. So the limit for this function is 0. You can graph it. You can also try all these numbers to see the tendency. I think by plugging 10 and 100 and compare, you can see the limit is approaching 0. That's question number 3. Any question? 3. So this one is no graph. It's very, very much a numerical question. We can try out all these numbers to estimate it. This one says use a graph to estimate the limit. I can do it with the this equal to. All right, so it looks like if we were to do a graph, you can also use number to graph.
Can we use the same numbers we did before on the problem before?
Which one?
Like how it just said plug in, like where you said plug in a 10 or 100.
Right. You should use at least 2 or 3 numbers to see where it goes to.
Okay.
So you can compare them. If you only use one number, sometimes that could be misleading. Graph that function, which is 1 minus 2 over x to the power of x. 2 over x to the power of x. You want to find the limit at infinity. Okay, a little hard to tell. Right, so I'm trying to see what's going on when x is really large. 0.11, furthermore, 0.1194, 0.1214. So it looks like we have a horizontal asymptote, but it's a little hard to anticipate what was the value. It says x goes to positive infinity. We can try a large number to tell. Correct it 2 decimal places. So we're gonna try numbers instead of looking at a picture. I can't really tell the picture, so I'm gonna use a couple of calculations. All right, so alright, so we're gonna do, says x goes to infinity. Let's do 2 or 3 numbers to see what it is. So we're gonna try x equal to 10. Alright, if x equal to 10, right, and what it is, it's gonna be 1 minus 2 over 10 to the power of 10, right? And I'm gonna try x equal to 100. Actually, we can just try a really large number because x is supposed to go to infinity. So it's gonna be 1 minus 2 over 1,000 to the power of 1,000. Right, so let me grab a calculator to do the calculation. 1 minus 2 over 1,000 to the power of 1,000. So I have this. That's our first number. And then there's an accuracy requirement. So I'm going to try one more time with 2,000. Just so that we can compare if we are accurate to decimal places. All right, you can try again with 2,000 in its place. If the number is the same as the first 3 decimals, then we're fine. If the number is much, much different, then we have to try another number. So let me try again with 2,000. So 1 minus, we're trying to find the limit when x is super, super large. That's why. Right, 2,000. I just want to tell if we are accurate. It says it corrected 2 decimal places. So let's say the 2 decimal places is stabilized. Let's try again, putting in 2,000 here. You can use your calculator. So I get this number. So it looks like it is accurate already to 2 decimal places. We try the 2,000 for the x value. Well, it changed the size of the so you can see they're very, very close already. Right now, it's accurate up to 3 decimal places. All right, so I'm gonna answer the answer. So it's gonna be 0.1. There's a 5 here. You can.
The 1, 2 now.
Yeah, it says correct to 2 decimal places. I guess 3 decimal places will be okay. Since it didn't say wrong to 2 decimal places, it says correct to it. So I'll just put 0.125 my. Oh.
It does 1, 2. 1.14. I have the same.
Oh, okay. Thank you. We have the same one.
Yeah.
Oh, yes. All right. So we round to 2 decimal places. So thank you.
The way we can do it.
Right. Correct. I mean, you did that. Not correct. I think it's more correct than 0.14. But anyway. Try your version. Do you have a different one or do you have the same? The same. Okay. So that's pretty much how it is. This gives us, well, all these practices trying to understand when we see x goes to infinity, what does it mean? It really means that x is taking on a really large number, a large quantity. And what people does in real life is we really can't make anything equal to infinity. So why do we calculate limit with x to infinity? Because you can anticipate what's going on when things go large. For example, if things goes this way, like population growth, right? You don't know what population growth eventually. You're gonna imagine if for a certain equipment, for certain construction, if the population is infinity, what will happen? So that allows you to anticipate a limit situation. Even though in real life anything goes to infinity is impossible, but we're still calculating it just to get a theoretical estimate out of it. This is question number 4. Let's see, number 5. All right. So this is the question. Do you have the same or a different one? Different. Mine have 2 times the exponential function. This goes with our calculation of the exponential function behavior. So we should apply what we mentioned here. So what we have here is a exponential function e to the negative, see what's the base, e to the negative 0.25. Okay, you can see it's less than negative 0.25. You can see that it's less than 1. So remember what happens when the base is less than 1, and we have it over here. This is when the base, other than the exponent, this is the base. If that is less than 1, you have a decreasing function. So at infinity, it goes to 0. Okay. So if you are using an exponential function, if the base, this is a base, e to the negative 3.35 is a base, which I calculated that is smaller than 1. So that's like a 70% growth every time. So 70% and 70% and 70%. So quantities are getting smaller. And then for e to the negative 35t is getting smaller and smaller. Its limit value is, see that, it's 0. This exponential function has limit 0, therefore the e to the negative 0.25t goes to 0. So 2 times it is 2 times 0. The whole limit is 9. So that's this one. You should have something similar, but depend on the base. If the base is positive, then it will be going to infinity. But if the base is negative, then it's the base is less than 1, which means the power is negative 2. Then it's to zero. Mine has a zero for the exponential part. That's my question 5. Do you have a different version?
Yeah, mine was 19.
Okay. So this is question number 5. Any questions? See, what is the next question? Alright, this one is a exponential function. We have a quite conceptual, but we're sure that b is bigger than 1. So the base is bigger than 1. The base is bigger than 1. The function goes this way. We don't know about the a. So this one, do have a horizontal asymptote, which is really the y equal to 0. So that one you write y equal to 0. That is a common horizontal asymptote for any exponential function. So I draw both of them on the board. See, this is an exponential function. This is a horizontal asymptote. That's the x-axis, which is also the y equal to 0 line. So this function going this way, horizontal asymptote is y equal to 0. This function goes this way, but its horizontal asymptote is still y equal to 0. Still, they're the same. For the logarithm, it has only a vertical asymptote because the logarithm is the inverse of the exponential function, so that's why they kind of go. This one is y equal to 0. This one is x equal to 0. So between the function and the inverse, we switch x and y. That should be question number. That should be question number 6. I think we're out of time. Hopefully they'll start you a little on your 1.7. That gives us a lot of practice over the infinity involving infinity. A limit involving infinity. Okay, thank you.
No.